Okay. Hello, everyone. Welcome back to the Topos Institute Colloquium. Today, we're very pleased and honored to have Samson Abramsky talking to us about duality for partial Boolean algebras. So please, Samson, whenever you're ready.
Okay, thank you very much, David, and thanks to you and the colleagues at the Topos Institute for inviting me to speak at this colloquium. So I hope everyone can hear me. If there's any problems with any of the audio visuals, please let me know. Let me just say before I start that as far as I'm happy to take questions during the talk, and particularly on any matters of clarification, it obviously makes sense to ask questions as they arrive. I believe there'll be some time available at the end of the talk for additional questions, maybe lengthier things, but basically I'm happy to take questions at any time. Okay, well, I'd like to talk about duality for partial Boolean algebras, and this is joint work with Ruiz Suarez Barbosa. As I will explain, I'll try and make this fairly self-contained. So partial Boolean algebras are structures that have arisen in the foundations of quantum mechanics. We'll see what they are in just a moment. If you're coming from the lens or the perspective of duality theory, another way of looking at this is it's a duality for a significant class of non-commutative structures. So the classical dualities of Stone and Gelfand and so on have been for commutative structures and spaces, and there's been a long-standing question about how to get duality for non-commutative structures where it's not clear what the spaces are. And this provides a very recognizable form of duality for a class of structures that correspond to some important non-commutative spaces. Okay, so the real starting point is the work of Kochen and Specker. They're the ones who originated the notion of partial Boolean algebra, and their work goes back to the 1960s. And really, they're sort of, in particular, it's associated with the issue of contextuality in the foundations of quantum mechanics. One of the key ways in which quantum mechanics is a non-classical theory in distinction to classical physics. I won't say a lot about contextuality, but just to give some general intuition, this arises because not all properties can be observed simultaneously. So the sets of jointly observable properties, those that can be observed together, provide partial classical snapshots. So each such collection looks classical inside itself, but there are many of these, and which can overlap, imposing sort of consistency conditions between them. And contextuality arises where you have such a family of data which is locally consistent, so you can patch things together locally, but globally inconsistent. There's no global description which recovers all these partial snapshots. This may sound to you a bit chief theoretic, and indeed it is. I'm not going to emphasize that aspect, but that is very much the sort of background thinking behind what they'll be saying. Now, the original kind of approach, structural approach to the foundations of quantum mechanics is the quantum logic of Birkhoff and von Neumann. So firstly, von Neumann, in his seminal work, which really pinned down the mathematical foundations of ordinary quantum mechanics, and his formalism is the one that's still being used today in many applications, but in particular in quantum information and computation. It's used on a daily basis. So he identified quantum properties or propositions as projectors on a Hilbert space. So we're not going to go very much into Hilbert space theory, and actually for our purposes, it will be sufficient to think of finite dimensional spaces, so essentially C to the n, where C is the complex numbers. Anyway, a projector on such a Hilbert space is a linear operator which is bounded, which we don't even need to say if it's finite dimensional, it's self-adjoint and idempotent, so simple algebraic conditions. And projectors correspond one-to-one to the closed subspaces of Hilbert spaces. The points that are left fixed by the projector form a closed subspace. which in turn uniquely determines the projector. So subsequently, after this foundational work by von Neumann, Birkhoff and von Neumann, in their famous paper on the logic of quantum mechanics, proposed the lattice of closed subspaces as a non-classical logic to serve as the logical foundation of quantum mechanics. And notoriously, this lattice is non-distributive, so many of the nice properties that allow lattices to support logics, be it classical or intuitionistic, simply don't hold in this quantum logic. And in this view, then, we interpret conjunction as the intersection of closed subspaces and the disjunction as the lattice theoretic supremum, which in terms of subspaces is the closure of the union. So we have to take the linear span and close it off. And as we said, distributivity notoriously fails in this. Now, this was the original approach of Birkhoff and von Neumann, and there's actually a vast literature on quantum logic. And it has to be said, or at least I'm going to say, not everyone would agree, that it hasn't really been all that successful as a working foundation for quantum mechanics, certainly as regards applications in quantum information and computation. And in fact, it's good to go right back to an initial sort of thing that arose in a basic postulate of Birkhoff and von Neumann, which is just to say that we have a notion, for example, of conjunction, which is to be interpreted on arbitrary closed subspaces. Now, if we think in terms of subspaces, of course, this seems innocuous because closed subspaces are closed under intersections. But if we think more operationally, linked to the physical meaning of this notion, then the corresponding projectors for two arbitrary subspaces, in general, which are really quantum operations that can be performed, they can be turned into measurements in a precise sense, a precise way. So unless they commute, they don't form a projector again. So in fact, the product of two projectors only form another projector if they commute. It's an if and only if. So if they don't commute, what is the operational meaning of this conjunction? And this was a question that I think has never really been well answered in that quantum logic tradition. Now, in their famous 1965 paper, Kochen and Specker set forth a different approach, where they used partial Boolean algebras. So rather than saying we have an everywhere defined conjunction and disjunction, the idea is that you make these partial operations and you only apply them where they are physically meaningful. That is where the projectors involved commute with each other. In other words, where they could coexist in a single classical snapshot, to refer back to our previous sort of brief discussion of contextuality. So we're representing incompatibility by partiality. And another way of saying it is we're representing a non-commutative structure, which is the algebra of projectors, by a partial, so the non-commutativity is represented by partiality. We only form the products where they do commute. And interestingly, there's a much later paper by Kochen, which develops a large part of the foundations of quantum theory in actually a very elegant and attractive way in this framework, with a notable caveat, which we'll return to. All right, so what is a partial Boolean algebra? So it's a structure where it's not, an important point is that there's not just partiality as the lack of totality, there's an actual piece of structure, a binary relation, which can be read as commeasurability or compatibility. So this is abstracting from the situation where we're only going to try to apply operations to elements in the algebra if they are compatible with each other. So this is, so concretely with projectors, this is when they commute, and abstractly we have a reflexive symmetric binary relation. So a reflexive graph where the relation is adjacency is read as commeasurability. And then we have constants, we have a total operation of negation, just like in a regular Boolean algebra. And now we have operations and an or, which are only defined on these compatible elements. So the domain of these binary operations are exactly the compatible pairs in the algebra. And so the key condition is that every set of pairwise commensurable elements is contained in a larger set of pairwise, a clique of the graph is contained in some clique which is a Boolean algebra under the restriction of the operations. So we can think of this as a family of Boolean algebras which can partially superimpose with each other and which cover the whole algebra. And these Boolean subalgebras of this partial structure correspond to the classical snapshots that we referred to earlier. And the key example to keep in mind, which provides the link with quantum, is the partial Boolean algebra of projectors on a Hilbert space, where commensurability means commutativity, and we have conjunction is the product, negation is the complement of the projector. So P, the negation of P is 1 minus P, where 1 is the identity. And so crucially, conjunction becomes partial, defined only on commuting projectors. And you can actually, there's a version of De Morgan's law where you put in the appropriate compatibility conditions. So actually from negation and conjunction, you can define disjunction and everything else. Now, morphisms of partial Boolean algebras are maps preserving commensurability and the operations wherever defined. And this gives the category of partial Boolean algebras. Okay, so now we can say what the Kochen-Specker, the famous Kochen-Specker theorem, I mean, the origin of contextuality. I mean, Bell actually, John Bell of Bell's theorem proved a similar result slightly earlier, but much less beautiful in its mathematical form. So here is the Kochen and Specker result. If we have a Hilbert space, there's an important dimensional condition. The dimension has to be at least 3. Then the partial Boolean algebra of projectors is such that there is no partial Boolean algebra homomorphism into the 2-element Boolean algebra. Now, if you are familiar with stone duality for Boolean algebras, I mean, this is a big deal. Every Boolean algebra has plenty of points. In fact, the whole idea of stone duality is to make a dual space from an algebra by taking the points. And here we're saying that for the things we really care about in quantum theory, there are no points at all. There are no homomorphisms of this kind. So what this says is there's no assignment of truth values to all propositions that respects the logical structure of the jointly testable propositions. So notice that we only have to, a homomorphism has to preserve conjunctions and disjunctions, but the only conjunctions and disjunctions we can form are those where the sort of arguments are compatible with each other. So this was in fact a crucial step that Kochen and Specker made. Von Neumann had proved the original hidden variable theorem in that 1930 book that I mentioned, but it had an unreasonably strong, it wasn't a convincing result because it had an unreasonably strong requirement for a hidden variable model, that it would be a total Boolean algebra homomorphism, preserving products even when they didn't commute. And then it becomes a rather trivial result, and there's no actual reason to require that. So this crucial weakening of the condition, the requirement, led to a strengthening of the result in this fundamental theorem. So there's no assignment of truth values to propositions which respects the logical structure of jointly testable propositions. And as we've said, this means that the spectrum of a partial Boolean algebra cannot have points. It's actually an empty structure, which is going to give a challenge for constructing a duality theory. So we can say that in a sense that, the Kantian conditions of possible experience, a phrase used by George Boole, which actually is quite related to Bell's theorem and so on. But anyway, we can say that this is conditions of impossible experience, because here's another way of stating the Kochen-Specker result. It's saying that there's a propositional contradiction and an assignment of elements of the partial Boolean algebra to the variables in the proposition, such that the structure satisfies that formula expressing a propositional contradiction. And what we mean by, and this propositional contradiction, in order to have this interpretation, what we're requiring is that whenever we form a conjunction, it's of compatible elements, and similarly for a disjunction. So it's a propositional contradiction where we can evaluate the formula at every step, only combining things that we can observe compatibly in the same context, in the same snapshot, and yet from a classical standpoint, it's a contradictory formula, and yet the structure satisfies it. So this tells us that the event algebra of quantum mechanics, which is what this P of H is, cannot be interpreted in a consistent fashion globally. Our local observations, real observations of real measurements, cannot be explained globally by reference to a single underlying objective reality. The values that we see have to be seen as inherently contextual. So how can the world be this way? And of course, this is still part of the ongoing debate about the interpretation of quantum mechanics. But it is a fact about quantum mechanics, which is a theory that's confirmed every day in scientific practice. Now, I want to make the point that this should be seen as quite a shocking fact. It's not, it's much more shocking than, for example, intuitionistic logic. In intuitionistic logic, of course, we're quite familiar with the fact that we can refute in intuitionistic models classical tautologies. I mean, the first idea of a Kripke model is that you can use it to refute P or not P. So excluded middle is not an intuitionistic theorem. That's quite familiar. However, you will never verify in any sound model of intuitionistic logic a classical contradiction. There's a well-known result, Glivenko's theorem, that says that. So in fact, so this reflects the asymmetric nature of intuitionistic logic. Just because, you can't just contrapose and use negation to swap things around, although you can refute tautologies, you can never verify classical contradictions intuitionistically. Every classical contradiction is an intuitionistic contradiction. And as a corollary, so that's a fact about intuitionistic logic. But as we've just seen, the Kochen-Specker theorem can be put in the form precisely that the partial Boolean algebras arising from quantum theory do verify contradictions. So, in fact, we can also see that partial Boolean algebras can behave very differently to the total case. It's a standard fact that every finitely generated Boolean algebra is finite. You can form disjunctive normal forms, say, from the things you started off with, and there are only finitely many of them up to logical equivalence. However, there's a beautiful result by Conway, not Kochen and Specker, but Conway, the famous Conway of Game of Life, etc., and Kochen showed that once you get to 4 dimensions, there's a set of just 5 projectors, local Paulis, which generate a uniformly dense infinite subalgebra of the whole algebra of projectors on C4. So, and they use rather beautiful, although obscure, geometric arguments to show this. I would like to find a more logical or combinatorial proof of that fact. Now, this category of partial Boolean algebras, we have a fact that every partial Boolean algebra is the co-limit of its Boolean subalgebras. But this has to be understood in the category of partial Boolean algebras, which is very different to its full subcategory of Boolean algebras. In particular, coproducts have a much simpler description in partial Boolean algebras than they do in Boolean algebras. You literally just glue together the disjoint union of the two things with identifying the top and the bottom, and no commensurability between the elements of one side and the other. Whereas to form the coproduct in the category of Boolean algebras is a bit like in groups. Since the operations have to be total, you have to sort of generate a lot of formulas that mix elements from the two sides of the coproduct. And anyway, one can show that this result holds, and there's a useful general construction which gives rise to, in various specializations, to colimits and so on, various other things that are useful, which is extending a partial Boolean algebra by extending the commensurability relation just by an arbitrary relation. And there's a universal way of doing that. And I don't want to go too much into details. I don't want to fall behind on my plan here, but one can give one could appeal to the adjoint functor theorem, but one can give a more direct constructive definition by building up something like a sort of term algebra, a quotient of a term algebra construction, but it's a bit more subtle because of the partiality. So you need to simultaneously inductively define when things are defined and when they're commeasurable, and then what the equations are. We can also so we can also use this to give an explicit construction of co-equalizers. Since we already have coproducts, this gives us colimits. Now, to understand what's going on here, I mean, Boolean algebras, the usual total Boolean algebras, are a full subcategory of partial Boolean algebras. And we know that any partial Boolean algebra is the colimit of its Boolean subalgebras. But then the cone from this category of okay, now we could given the diagram of Boolean subalgebras of the given partial Boolean algebra, which I'm calling B, we could form the colimit in the category of Boolean algebras, which also perfectly well has colimits. And then there will be, because I mean, the cone from D to B, from this diagram of Boolean subalgebras to D, is also a cone in partial Boolean algebras, and hence there's a mediating morphism. Sorry, I've been saying the wrong names here. The partial Boolean algebra is A, but B is the total Boolean algebra, which is the colimit in the subcategory of Boolean algebra. So there is a mediating morphism, and therefore there would be a morphism to 2, because from any Boolean algebra there's always a homomorphism into 2. So what's going on? Well, to resolve this, we know that we're taking Boolean algebras to be an equational variety, so it includes the one-element Boolean algebra where true equals false. And of course, that trivial Boolean algebra does not have a homomorphism to 2, and it's something which we know very well. It's, if you like, the Lindenbaum algebra of any inconsistent theory. So what this is saying is that the colimit of its diagram of Boolean subalgebras must be this inconsistent Boolean algebra. So to speak, we're holding all these perfectly good Boolean subalgebras together in this diagram. When we try and merge them and force them to be a single Boolean algebra, we generate an inconsistency and collapse into the one-element Boolean algebra. So that's what happens if we evaluate the colimit in Boolean algebras rather than partial Boolean algebras. So it's, so to speak, that by holding things apart, by not making the operations total, respecting the commensurability relation, we're able to keep a consistent structure. But if we try and interpret everything globally, then it collapses. So we could say that a diagram is implicitly contradictory if its co-limit in Boolean algebras is this manifestly contradictory thing, and then a partial Boolean algebra with a Kochen-Specker property, such as the projectors, holds this implicitly contradictory information together in a single structure. Okay. Well, I think I'm not going to dwell on this. I'll say a bit about the tensor product, because this is an important point. The Kochen-Specker property arises in P of H as soon as the dimension of H is at least 3. If we look at the projectors on C2, we can actually describe them quite easily as, because the point is in C2, once you give me one non-trivial subspace, one-dimensional subspace, which isn't the whole thing, there's a unique orthogonal. And so the sort of bases are going to generate the 4 copies of the 4-element Boolean algebra. And the whole thing, in fact, can be described as a big co-product of copies of this 4-element Boolean algebra. That is easy to see that is although that is, that's easy to see there are plenty of homomorphisms into 2 from that, because obviously for each 4-element Boolean algebra, you just sort of choose which of the 2 sort of points in the middle you assign to true, and then you get a well-defined homomorphism into 2, and then you can use, since it's just a co-product of these, you can glue all of these together, and you're perfectly good with a homomorphism into 2 of the whole thing. And so that, if you like, there is a hidden variable model in the 2-dimensional case. Now, one of the key points at which non-classicality emerges in quantum theory is in passing from this P of C2, which does not have the Kochen-Specker property, to P of C4, which is P of the tensor product of 2 copies of C2, which does. And the question is, can we capture the, oops, oh no, oh dear, I've lost, how do I resume my sharing? I tried to get rid of
You seem to be sharing from my point of view.
Oh, okay.
At the top of,
unfortunately. Is there something I can...
What are you seeing? Are you on the Zoom screen?
I'm just seeing myself, unfortunately.
Yeah, look at the top, you might see some tabs. Samson screen. Can you click that one or something? I don't know. Or you could try unsharing and resharing, but we see your screen fine. We see the question. Yeah.
Sorry. Let me full screen. Oh. Sorry about that. I just wanted to get rid of the sidebar. How do I have to stop the share and start it again. I'm really sorry about this.
No problem.
Okay, all right. Can you see it now?
Yep, we see your question.
I can see it now too, so that's good. All right, so okay, so we have this emergence of non-classicality once we take the tensor product of 2 copies of C2. So if we could, we could capture this in logical form if we could capture the Hilbert space tensor in logical form. And so this can be expressed in the categorical terms as saying, is there a monoidal structure on the category of partial Boolean algebras which is strong monoidal with respect to the functor that takes a Hilbert space to its partial Boolean algebra of projectors. And this is this would fill this. This would really allow Kochen's program of axiomatizing quantum mechanics through partial Boolean algebras really complete that and give a complete logical, give a sort of compositional logical characterization of quantum theory in a form useful for quantum information and computation. So I think it's a very intriguing problem. Alas, I don't yet have an answer to a full answer to this. We have some approximations. So let me briefly say something about that. I'm conscious of the fact that time is passing, but there have been candidates for tensor products of partial Boolean algebras. Already in the work of Hernan and van der Berg, it was shown there is a natural monoidal structure on partial Boolean algebras where you range. Remember that a partial Boolean algebra is the co-limit of its Boolean subalgebra. So you take the co-products of the subalgebras from the two things, and then you take a co-limit of that family. Using the existence of co-limits that we mentioned earlier, which they've proved by an appeal of the adjoint functor theorem, and we can prove a bit more explicitly using the inductive construction I showed you previously. So particularly you take the co-product and then you sort of introduce the commensurabilities you need by means of the universal construction that I went over rather quickly before. So this is fine, it all works, but it's not exactly what we want. There is a lax monoidal functor of the kind we're looking for, and an embedding of the actual tensor product of an embedding of this tensor product, as we've just defined it, on the partial Boolean algebras arising from the Hilbert spaces H and K into the projectors on the Hilbert space tensor product of H with K. But it's easy to see that this embedding is far from being surjective. And in fact, in the simple example we showed earlier, there are many two-valued homomorphisms on the two-element on P of C2, but there's no such homomorphism on P of C4. There is, so anyway, this is a lacuna in the argument by Kochen that I mentioned earlier. And the problem is that the nature of the lacuna is that, you know, he's using the identities that arise in the actual Hilbert space H tensor K, and there are more relations that arise from that at the level of the projectors, at the level of the partial Boolean algebra, than arise from the construction we just gave on partial Boolean algebras. So this poses a challenge, a kind of axiomatic challenge. Can we find the additional relations we need on the partial Boolean algebra we construct to make P of H tensor P of K that will be, as it were, a complete set that will fully characterize the tensor product of Hilbert spaces? This is something that can be partially resolved, but we haven't fully answered that question yet. As I say, it would be a sort of the final step in a rather complete reconstruction of quantum mechanics, which makes it a tantalizing problem. So here's a step towards a more expressive tensor product. The sort of way we've defined things in that, I mean, it was in the universal construction was rather conservative. If we had projectors, say P1 tensor P2, Q1 tensor Q2, to ensure they commute, we need the conjunctive requirement that P1 commutes with Q1 and P2 commutes with Q2. But to show that they're orthogonal, we have a disjunctive requirement, because if you just have P1 orthogonal to Q1, then even if P2 doesn't commute with Q2, if you multiply them, then the first component vanishes, P1, Q1, and since tensor is bilinear, that will kill the whole thing. So even though P2 and Q2 are unrelated, you're still going to get this orthogonality, and hence, in particular, commutativity. So the idea that propositions can be defined on quantum systems, even though sub-expressions are not, is indeed emphasized by Kochen. So we can get at this by talking about a logical exclusivity principle. We can say that two elements that need not be compatible can be said to be exclusive if there is some element they definitely disagree on. There is some C such that A entails C and B entails not C. And here the entailment is the usual thing in a partial Boolean algebra, but we require that, that the two things have to be compatible. So in a partial Boolean algebra, this orthogonality is a weaker requirement than just saying that A and B entails a contradiction, although the two would be equivalent in a Boolean algebra, because these two events don't need to be commensurable. And we say that a partial Boolean algebra satisfies the logical exclusivity principle if whenever two things are logically exclusive, they are in fact compatible. So this is a strengthening of the axioms of partial Boolean algebras. And importantly, it's valid, as you can easily check, in the partial Boolean algebras of projectors. In fact, it's equivalent to another well-known principle, which is just to say that the entailment ordering induced in the order structure of the partial Boolean algebra really is an order, in particular that it's transitive. You can't infer that the order as we defined it here is transitive, because we may not get, if you have x less or equal to y, y less or equal to z, we don't know a priori that x is compatible with z. And it's equivalent to saying that if, transitivity holds, that this logical exclusivity principle holds. And any so the projector partial Boolean algebras always satisfy this principle. And we can form the partial Boolean algebra where we've extended with this relation of orthogonality, we're extending the compatibility to include orthogonality. We get an adjunction, and so we can sort of force the logical exclusivity principle on any partial Boolean algebra. And there's a universal property that goes with this. And this is a sort of simple variation of the general inductive construction that we showed earlier. I mean, we could reduce it to the adjoint functor theorem. We get a more explicit description from this inductive construction. And we can use that to make a logical exclusivity tensor product. So we can ask then how close it gets us to the Hilbert space tensor product. But unfortunately, it doesn't really get up, it gets us up the tree, but not to the moon. We don't get the Kochen-Specker property if we didn't have it before. Right, so that remains a tantalizing open question. The subtlety of it is the interplay between equations, the additional relations we need, and definability. As you get more equations, you can also increase the commensurability relation, which then lets you define more things, which then gets you more equations. And it's capturing that interplay between them that is quite subtle. Okay, so I hope I still have enough time, I haven't left myself very much, to get to this duality for partial Boolean algebras. So we want to get a duality theory, and at first sight, this looks hopeless. The classical stone duality for Boolean algebras builds the stone space of the Boolean algebra from its points. In other words, the homomorphisms into two, which, when you turn things around under a contravariant duality, are going to give you the continuous maps from one into the stone space of B. In other words, the points in the usual sense. But as we've seen by Kochen-Specker, for exactly the interesting cases of partial Boolean algebras, there are no points. So instead, we're going to generalize another classic duality for, in this case, complete atomic Boolean algebras, the Tarski or Tarski-Lindenbaum duality. And we'll see that we can get a duality theory for complete atomic partial Boolean algebras. So just to remind, a Boolean algebra is complete if it has arbitrary joins and hence also meets. An atom is a minimal non-zero element. In the world of propositional calculus on a finite number of letters, an atom in the sort of corresponding Boolean algebra is a state description, as Carnap called it. It's a big conjunction of literals that tells you for every variable whether it's true or false. Whereas on the other hand, if you took the full propositional calculus with infinitely many letters, it's atomless because you can't form infinite conjunctions. So a Boolean algebra is called atomic if every non-zero element sits above an atom. And a CABA is a complete atomic Boolean algebra. So the classic Tarski duality, or Tarski-Lindenbaum, says that there's a duality between CABA and a contravariant duality between CABA and set. And it's given essentially in both ways by the power set construction. So if you take a set to its power set, then the singletons are going to be the atoms, and then on morphisms, we get the power set relation, we get the power set functor, which contravariant power set functor, which takes the inverse image of a function. Now, going in the other direction, to make this into a full duality, you map a complete atomic Boolean algebra to its set of atoms, and on morphisms, a Boolean homomorphism is used to define a relation. We define a relation mapping an atom Y of B to the unique atom of A such that Y is less than or equal to H of X. And the uniqueness is then argued in using the properties of atomicity. And it's because there's a unique such thing that you get a function. And that's why we get a duality between CABA and set. Okay, so how do we transfer this to the world of partial Boolean algebras? So obviously we want to have joins of compatible subsets, cliques of the graph, and a partial Boolean algebra is called atomic if every non-zero element, and by the, actually I should say here that we're going to be interested in these transitive or partial Boolean algebras, those corresponding to having this logical exclusivity principle. So there is a real partial order there, which is defined on the partial Boolean algebra. So we just put these concepts together and we get the notion of a partial CABA, a complete atomic partial Boolean algebra. And again, P of H is a partial CABA. Atoms are the rank 1 projectors or one-dimensional subspaces, which correspond to the pure states in quantum mechanics. So the key idea in setting up this duality, so if you as we were saying, if you think of it as a non-commutative duality, what's going to replace the space of points? Well, we're having a duality with atoms, and the idea is to replace sets by graphs. And the adjacency in these graphs are going to generalize the as logicians call it, the apartness relation, the not equals relation. And thus a set will embed as a complete graph. If you like, everything is compatible, everything is sharp, and we can distinguish between arbitrary elements. So these exclusivity graphs are the non-commutative spaces in this duality. So notice that the natural thing, if we say this, is that this is going to be an irreflexive graph. And morphisms are graph of certain relations, generalizing the functional relations which appear in classical Tarski duality. As we said here, in the first instance in Tarski duality, you define a relation, and then you use the properties of atomic Boolean algebras to argue that actually the relation is the graph of a function. But that's 2 steps. The second step is no longer valid in this strong form, and we have to weaken it to get the right notion of morphism. So a graph is going to be irreflexive graphs. These are going to be the exclusivity graphs. And then we have some operations. I'm not going to. I think I'm running out of time, so I will not Don't worry, David. So I won't dwell on details, but I just want to convey the main ideas. So obviously, cliques are sets of pairwise adjacent vertices. And then the graph of atoms of a partial Boolean algebra has as vertices the atoms and edges exactly those things that are logically exclusive in the sense that we defined earlier. And we can interpret these atoms as worlds of maximal information and incompatibility between them. If A is a Boolean algebra, then at of A is going to be the complete graph on the set of, because, different atoms are always, their meet has to be zero, right? They have complete information. If they're distinct, they will contradict each other. So you will get naturally the complete graph in this way. And in a CABA, every element is uniquely written as a join of atoms. In a partial Boolean algebra, this set of atoms may not be pairwise commensurable, hence their join need not even be defined. But what we can say is that for any maximal clique in a Boolean subalgebra below an element, then the join of those atoms below it in any clique does give you back that element. So any element is a join of any clique that is maximal. And given any two maximal cliques, this yields an equality even where the elements in are not commensurable. And the key to reconstructing a partial CABA from its atoms lies in characterizing such such cliques and when we do get this equivalence. And this can be given graph theoretically. So this hash, without going too much into details, but it's about the neighborhoods. It's a graph theoretic, combinatorially defined notion, just the sets of adjacent things to, for a set, it's the common neighborhood of the elements in the set. Okay, so we can build, so the point is we can reconstruct the whole algebraic structure of a partial CABA from its graph of atoms. This is, so once we've got the equivalence, this becomes fairly straightforward. We can do things by representatives. And to get a full duality, we need to isolate the conditions on an abstract graph, which doesn't come originally from a partial Boolean algebra, which allow for such reconstruction. So that means we can pick up an abstract graph in our category on the other side of the duality and build a partial Boolean, a partial CABA from it. And so we have a couple of conditions that arise quite naturally. The main one is the first one. So what this is saying is if X is adjacent to everything in some set and Y is adjacent to everything in some other set, then X is not equal to Y. X is adjacent to Y. That's the main technical condition, which is kind of illustrated here. You see the X and the Y, and yeah. So, and a complete exclusivity graph is a graph such that, So a helpful intuition is to see this as generalizing sets with an inequality relation. So a graph is symmetric and irreflexive, and to be an inequivalence, we need cotransitivity, sort of just by dualizing the usual transitivity. So the first technical condition is a weaker version of cotransitivity, and the second one eliminates redundant elements. Anyway, this is the sort of technical part, but the result goes through that if A is a partial Boolean algebra, then indeed we land in these complete exclusivity graphs when we take the atoms. And the other part is to get the morphisms. These are going to be relations now between graphs. and again, we're sort of dualizing using inequality to generalize from the conditions that would define a relation being the graph of a function. So, and so these are natural generalizations of those conditions. Okay, so, and this is how we define the relation, exactly the same way as in the classical Tarski case. It's just that this will now be in a relation and not the graph of a function, but it will satisfy the properties you see here, the sort of coherent properties that are relating how we relate to each compatible island within the whole structure. Yeah, okay. I think I'm gonna. I mean, so the machinery of duality theory goes through with these constructions, and we get a full duality here between the homomorphisms of these partial CABAs and these graphs, exclusivity graphs and graph morphisms. And in fact, this gives us another, I mean, people, looking at graphs is very standard in Kochen-Specker constructions, and this is recovering in a more conceptual way exactly where these kind of graphs come from. Okay, I'm sorry for rushing at the end, but I wanted to finish more or less on time. I mean, just to say that, so we do get a full duality between partial CABAs and these exclusivity graphs, and from that we can get I mean, if you take the classical case, we also get a free forgetful adjunction, which builds the free CABA by a double power set construction, which, roughly speaking, you can think of this as giving you a sort of set normal forms for complete atomic Boolean algebras. A huge, if you like, in general, a large, say, disjunctive, disjunction of conjunctions of literals, essentially. This is something you can read off as a free forgetful adjunction between CABAs and set from the Tarski duality, just using the fact that the power set gives you, sort of flips you between set and set up. And we can do the same thing for partial CABAs. We would like, I mean, we have a reasonably explicit description of the free CABA, but actually we would like to get a better description, which hopefully will help with that tantalizing problem I mentioned earlier of pinning down the relations we need to capture the tensor product in a compositional fashion. Okay, well, thanks for your patience. I'll stop there. Thank you.
Thank you, Samson. Okay, so if you have questions, feel free to raise your hand or just unmute yourself and you can ask.
I see one hand.
There are some claps, but no hands yet.
Oh,
I was wondering if you could make a connection between kind of your Bell's theorem, sheaf theoretic stuff and this. Is there any way to talk about what the open sets might be, or what any kind of connection?
Well, I mean, yes. In fact, I mean, that needs to be developed more. But I mean, this is also why it relates to this free forgetful adjunction, because can build the partial Boolean algebras from a sort of sheaf model of contextuality, essentially by applying a free construction here. And in general, the partial Boolean algebras you get will not have the Kochen-Specker property. And indeed, part of the geography of this whole area is that the Kochen-Specker property is a very strong property. And there are lots of forms of non-locality and contextuality which are weaker than that. So in a general setup where you can describe all of those, then you won't get the Kochen-Specker property. And understanding the boundary of where you do and how to go from, between these situations is, I mean, that's an interesting and still developing area. But yes, you can go from a sheaf. And we had an earlier paper with Rui where we did discuss this more explicitly, so that you can start from a sheaf model, go to the extract the partial Boolean algebra, and then what we called empirical models become states defined on the partial Boolean algebra, which are assignments on the partial sort of measures essentially on the partial Boolean algebra, and so you can translate things into that
Okay.
language.
Thanks. It looks like we have a question from Corinthia, so please go ahead and unmute.
Hi. First of all, great talk. So you mentioned that kind of the straightforward attempt to generalize stone duality fails for partial Boolean algebras. I was wondering if you could get potentially an analog of the stone embedding theorem, which, if you think of it as saying that every Boolean algebra embeds in a complete atomic Boolean algebra, then it seems like the sort of analog of that for this would be every partial Boolean algebra embeds in a complete atomic partial Boolean algebra. And so I wonder if you've like thought about that at all, or have any like immediate thoughts about why it wouldn't work.
Yeah, that's interesting. Well, the earlier result I mentioned was about this universal construction, which would, for example, take you from a general partial Boolean algebra to one satisfying this logical exclusivity principle.
Yep.
And so the unit of that adjunction is going to give you an embedding into that. We didn't, I mean, it's a good point. We didn't consider the thing about whether you can embed an arbitrary partial Boolean algebra into a partial CABA. That's a good question, and we should think about that. Yes, thank you.
Yeah.
I mean, by the way, a reaction I've encountered is, I mean, people used to Boolean algebras, think of CABAs as a bit boring, because they're after all, they're equivalent to set, and topologically they're not very interesting. So we're absolutely interested, in sort of things where you have additional structure. But on the other hand, it is also worth insisting that from the quantum point of view, the most interesting examples are these projection partial Boolean algebras, which are indeed complete and atomic. But still, anyway, so for all the more reason for considering the question that you've raised. So thank you for that.
Thank you.
Okay, thanks, Corinthia. I guess we have time for one more quick one, if there are any.
I mean, as we discussed earlier, David, if anyone does have any additional questions, I'm happy to stay on for a few extra minutes. Obviously, the sort of formal session ends in, I guess, very soon.
Yeah.
But,
so maybe we'll stop the recording in the live stream as soon as I can press the relevant buttons, and then if anyone wants to stick around. But thanks again, Samson, for your talk.
My pleasure. Yes, thank you.
So did that one more. Okay, we are now just the 16